Properties are number 1. Now comes the properties. If f is continuous, then f is integrable. If it's continuous, then f is integrable. Okay, continuous on a comma b. So understand, if f is continuous on a comma b by extreme exterior interior theorem, extreme value theorem, whatever it is, I think exterior interior theorem, f achieves the maxima and minima, f is bounded, okay, and hence f is bounded and also f is continuous. So using these conditions, we get that f is integrable on a comma b. So continuous functions on a closed interval are integrable, okay. This is what we have got about the properties of continuity. Let's see what we can do more. We'll see a function which is not Riemann integrable. Function which is not Riemann integrable are integrable is Dirichlet function, are integrable. So what is Dirichlet function? Fx is equal to 0 if x is rational and 1 if x is irrational. So if you take fx on 0, 1, understand that, let's prove it. For every partition xi, xi plus 1, for every partition, the small mi will be what? The small mi will be 0 and the capital Mi will be 1 for every partition. Whatever small you take, however small it is. Since, why? Because between every two numbers, there is always a rational number and a irrational number, right? So whatever small value you take between every two partitions, Mi, the height will be 0, the minimum height will be 0, and the maximum height will be 1. For whatever small any points you take. Okay. So therefore, understand this very carefully. Therefore, what will happen? The lower sum, each of the element will be 0, and the upper sum will be what? For every partition, the upper sum will be what? U of, let's say, p. For every partition, upper sum will be what? Summation of mi xi plus 1 minus xi, let's say. Mi is 1, so you get summation of xi plus 1 minus xi, right? So what will you get? You will just get, if you just do it xn minus 1 plus xn minus 1, you will just get xn minus x naught, which is 1 minus 0, which is 1, because the limits are 1 minus 0. This is a and this is b. Here it's a and b are 0. So you get the up, the upper sum, uf, for all the partitions, it's 1. So for inferior, it's also 1. So therefore, we get the function ka the lower sum is 0 and the upper sum is 1, and it's not equal, and hence it's not integrable. There are very pretty basic properties out there. The basic property is that if f is bounded, then we define that, not define, but it's integrable on like this AB fx dx is just bounded, okay? Just bounded will have is done. Then it's integration. Then you can write as a to c fx dx plus t to b fx dx. Okay, you can write like this. If it's just bounded and c belongs to an internal point and f is integrable, then we can write like this. It's an if and only if. So if we can write like this, then also f is integrable on this. Okay, that's the idea. So this is property number 1. We will not prove this because we will take days and weeks to prove it. Okay, I mean, if we do all the proofs, I'm just telling you all the results. You can see the proof from. So now comes the algebra. Okay, the algebra of the functions. I will just give a screenshot of all the properties because I don't want to waste time. And these are pretty easy to prove stuff. Algebras are the following. So I will just scroll through the results. If f and g are integrable functions on the interval, this is the algebra, okay? Algebra of the integrable function, which I told you algebra is very important. Algebra of integrable functions. Because this helps you to integrate more and more functions. If f and g are integrable, then f plus g is integrable and it's defined as this. For k, a function is just constant and that is integrable and it is defined like this. If f is between the maxima and minima, then it's, observe this is true. This is very easy to understand. Why? Because it's like telling fx is less than equal to m and greater than equal to small m. So therefore, you can just do integration. This is less than equal to m. So integration 1 dx, that is b minus a, integration m. So it's like, that is understandable, right? If fx is less than equal to gx, then this happens. And if f mod x is integrable, if fx and mod x both are integrable, then its modulus value is less than equal. This is a triangle inequality. Okay, why? Because summation, if you remember, summation of ai ka mod is less than equal to summation of mod ai, right? And imagine that integration is nothing but a summation, limiting of summation. So we can actually take the limit and also say like this, okay, if the limit exists. So that's why if the limit exists, then this will converge to mod f and this, right? So it's just an application of triangle inequality. So these are important because understand, often it's very hard to calculate the integration, okay, because the function is very bizarre. So we need conditions like this to approximate the function so that we can get a good idea about the function. So we need these properties out there which are important. Okay. So there's another definition. Okay, there's another definition. Two definitions are there. Integration a to b fx dx is minus of integration b to a fx dx, and integration c to c fx dx is equal to 0. In some sense, the length is 0, and here it means that if you consider this minus dx, then it's fine. It's like here when you're going from a to b, you're taking positive, 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 positive. So here you're going from b to a, you have to take negative dx, negative dx, negative dx. So it's integration fx times negative dx, negative dx, negative dx when you're going from b to a. So you can think about like this. It's a definition, okay? It doesn't mean anything, but it's a definition. It helps you to compute things easily. So these are two definitions.